Hi folks, Buckley here, lecture number 19 in MEEG102. Today we're going to talk about design validation. It's part 2 of a 3-part series. So, in lab, you guys are working on virtual Lego crushing using the Finite Element Analysis tool in SolidWorks, which is super exciting. Again, we have lab this week, online lab number 8. It's your last lab. Those of you on Tuesday already went. Thursday, you're going now. Individual assignments. Assignment number 6 is due this week, okay? Then you're done. You are done with your individual assignments, so congratulations. Design project, milestone number 9, happens this week. It is a 1-week assignment. We don't expect you to be all the way through design validation, but we expect you to have a good chunk of it done, okay? Final presentations are next Thursday, the 14th. And we'll make sure that we announce the schedule of the presentations by the 11th, by Monday the 11th. So you'll know exactly what time slot you're presenting in, as well as there'll be a little bit more information about other expectations, like you sitting in and reviewing other people's presentations. Honors folks, again, your last thing for me is a maker profile. Again, I'm hoping to get that grading done for you really shortly on your second set of comments on the reading. But last thing for honors folks is the maker profile. Live sessions with me, those are Tuesdays and Thursdays, 10:30 to 11. Always like seeing you guys. It's a good reminder that we're all still here in person, even if the lectures are delivered virtually. Okay, just one thing to start. So I'd like to pick up where we left off last time, which is your class participation from last lecture was this case study, a golf ball launcher. So I'd like to work through this problem. Let me just reread the statement. Hopefully you gave it a good, honest effort, and we can now work through it together. So case study number 2, golf ball launcher. For your class project, you and your team are designing a spring-powered golf ball launcher for ages 6+. You want it to be powerful enough to launch a golf ball vertically at least 10 feet in the air. The tube for the launcher is approximately 2 inches in diameter. Inner diameter, and the latch for the spring can be pulled back up to 3 inches for launch. Choose an appropriate spring for this application from the McMaster-Carr catalog, and remember that you only have $20. So let's say that you are actually making this thing and we didn't have the spring that you needed in the design studio. We have a lot of springs, but maybe not this one, and you had to order it special, okay? So let's get going on this problem. We're going to start with a general understanding of the principles involved. So let me hop on over to the document camera, okay, and we will talk about what's involved here. So you've got yourself, the launcher is going to be firing vertically, right? So we're going to pull this guy back. It's going to compress a spring. There's a ball in here. It's a golf ball that then launches vertically. And the height that we want the ball to launch, so the situation at first is going to be a compressed spring, right? So there's a compressed spring with a ball sitting on top of it, okay? And the energy here is stored in the compressed spring. And then what's going to happen is that is going to stretch all the way out, okay? And just like the rubber band, this is the point at which the rubber band would release. This is the point at which the ball is starting to actually move, so we would have some initial velocity, VI, okay, and the energy here is all kinetic. So this is elastic potential. This is kinetic. And what's going to happen is the ball is going to travel, and we want it to travel up a maximum of 10 feet, okay, before it starts to make its way back down. So it's going to get up to 10 feet, and then it's going to kind of hang there. So at this point, we have all gravitational potential. And you might ask things like, oh, well, you know, how long is this tube? Maybe that's eating into some of this height. We're going to ignore that for right now, okay, and we'll take care of that with a factor of safety. So what we're going to do is we're actually going to skip this middle step here. So in a conservation of energy expression, I would advise that we set the elastic potential down here equal to the gravitational potential at the top. So we're going to go, elastic potential is 1/2 K stretch squared. We've been working with that expression a lot, equal to, up here, we're just going to have mgh, right? Where S is the K equals spring constant, That's something we can set when we purchase our spring. S equals spring stretch. The M is the mass of golf ball. And G is our gravitational constant, okay, which I'm actually going to, just for giggles here, work in the American system, okay, which means that actually the mass of the golf ball, if you look it up, it's 1.62 ounces. Okay, this is still a force, so I'm actually going to convert that into this unit called slugs, all right, which is 3.15 times 10 to the -3 slug. Slug is a unit of mass associated with the with pound. Okay, so G times 1 pound is, or I'm sorry, 1 pound is equal to G times 1 slug, right? So we'll work in slugs just for fun. G is equal to 32.2 feet per second squared. So we're going to work in the foot pound slug unit system here, okay? So just for fun. But if you prefer, you can convert all this to metric and then work your way backwards. The reason actually I'm going to work in the US units is because McMaster-Carr mostly lists its spring in the US units. Okay, so we have to we need H. H is equal to 10 feet, right? We want a 10-foot shot distance. Okay, so we need another input here. So if I have MGH, cool, I'm okay on that side of the expression, but I still have K and S here that are both variables right now. So what I'm going to do is I'm going to leave K as a variable, and I'm going to make an assumption about S, because I have some information, right, which is that basically you want to pull back this spring. Maximum is going to be 3 inches, but let's say we pull it back 2.5. Okay, so I'm going to say that S is equal to 2.5 inches, which is equal to 0.208 feet. All right, 0.208 feet. Okay, so now all that I got left to do is solve. So I'm going to rearrange this expression in terms of K. So when I do that, the 2 flips over, right? The S squared is going to flip over. So I have K equals to 2mgh divided by S squared. And then I'm going to plug all of this in. So when I do that, I wind up getting K is equal to 46.9, and the units here are pound per foot. Okay, so that would be what I need to drive this up. Now, I'm going to go now and I'm going to look on McMaster-Carr. So I want a spring with a spring constant that is equal to or maybe a little bit greater than this. I also want an outer diameter of my spring needs to be less than 2 inches to fit inside the inner diameter of that tube, right? So my spring is going to be constrained to fit in there. And then the other thing that is going to be important is the length, right? So if I want this to have 2.5 inches of compression, the spring is going to need to be, the compression spring is going to need to be much longer than 2.5 inches, right? So a compression spring, they're going to, eventually it's going to kind of tighten down on itself. Okay, so I'm going to need a spring that's fairly long. All right, so let me flip over to McMaster-Carr and actually see what I have. And actually, I'm going to take one more step. I'm going to go ahead and convert this into pounds per inch. So this winds up being 3.91 pounds per inch, because this is actually how K is rated on McMaster-Carr. So let's go over to McMaster-Carr and let's go spring shopping. Okay. So here we are in McMaster-Carr. I'm going to type in compression spring. All right, I'm going to be working in the inch system. Now here's where things get interesting, right? So if I go ahead and I say I want a 2-inch or exactly 2-inch spring. Let's watch what happens. So I'm going to go a little under 2 inches. I'm going to make that the first thing that I decide, 1.95 or 1.96. Okay, that's going to give me springs that are going to be really, really stiff. Okay, so this is a really heavy duty, massive spring, and that's not what I want. That's going to be a problem for my users, right? So actually what I want to do is I'm going to take a compression, straight up compression spring. There's different end types. For this kind of application, you'd probably want a closed or closed and ground end. We don't need to select that necessarily right away. What I'm going to do next is, you notice there's options for shopping here on length, compressed length at max load, wire diameter, okay, the rate, this is the stiffness, right? I'm actually going to go here and I'm going to first deal with the length issue because I want a fairly long spring. So I'm going to come down here to springs that are about 5 inches long. You could pick different ones. Okay, so this is 5-inch long spring here. There's multiple answers here, folks. Okay, so your job is to find a spring that's going to get the job done for the budget. Now, rate, we have options here too. So remember, I want to exceed 4 pounds per inch. So I could go here with an 8 pound per inch, 8.5 pounds per inch rate. 5-inch long, it's 1.225 outer diameter, so that's going to fit nicely inside of that tube. Compressed length at max load, it's going to go from 5 inches to 1.2 inches. Okay, so that gives me 3.8 inches of travel, which is plenty of travel, right? So I'm actually going to go with this part. So if I were using this in my design, I would actually go into the product detail, right? I would look at this information and then I would probably download the CAD file so that I could incorporate it into my, my assembly, right? So I'm liking this spring. You guys may have found another one. Okay, anything that is kind of within range in terms of length, outer diameter, and stiffness we're good with. Note that I didn't select a dead-on 4 pounds per inch spring. Okay, so you can have a little bit of a factor of safety. So this is about twice as stiff. Now, I'm going to flip back to the document camera because I do want to do one final check, which is if I'm going with this spring type, I want to make sure that I can actually pull back on this spring and get the height that I want. So I'm going to rework with this expression here. Okay, and I'm going to say in this instance that my K is known. K is going to be 8.5 pounds per inch, or equal to 102 pounds per foot. Okay, everything else is the same. M, G, and H are the same as before. And now what I'm going to do is I'm going to go and I'm going to back solve. I'm going to back solve for what the stretch is. Okay, so what's the stretch needed to cause this? Okay, so my expression again is 1/2 KS squared equals MGH. So solving for S, I'm going to get S is equal to, this flips over, so 2MGH over K square root. If I plug in all of my values, I wind up getting a stretch of S is equal to 0.14 feet, which is equal to 1.7 inches. Okay, now I want to check, can a user who's pulling this back 1.7 inches, can they actually apply enough force? Because that's a fairly stiff spring, okay? So to check on the force needed to cock this guy back, I would use the expression, the force is equal to K times the stretch, right? So how much force is the user going to need to pull back on this little lever, right? So there's a little lever that needs to be pulled back by the user to cock the launcher. Okay, so this would be 8.5 pounds per foot times, pounds per inch, 8.7 pounds per inch times 1.7 inches. So they would need to apply 14.5 pounds in order to cock back the gun. And that's reasonable. I mean, this is a toy that might be a little hard for a 6-year-old, but for an adult, which is probably going to be the primary user for launching golf balls, this would be totally fine. This is worth checking. This user standpoint here, right, is worth checking, and we're going to get into it in our last workshop together. We'll talk about the user standpoint on those rubber band shooters. How easy is it to pull the trigger? Okay, so you do want to check, you know, you can make something that's going to launch that golf ball really, really high, but it's going to be incredibly difficult for a normal person to actually use that system. Okay, I want to take a step back right now and think about what was important in this problem, okay? So the first thing that was important is we had some underlying principles. We boiled down the design challenge into some fundamental principles, and they were related to conservation of energy, right? So that's number one. The second thing is we were really clear about what were our knowns and unknowns, what things are left to us to design. We made some logical assumptions. So my first assumption was the amount of spring stretch that I was getting, right? And then we came up with design parameters calculated, right? So we have a goal of more than 3.91 or more than 4 pounds per inch that we're looking for when we're going shopping. Then we go shopping, right? So we go out there and we try to find what is stock. I'm not going to custom order a 4 pound per inch spring that is 5 inches in length and just under 2 inches in diameter, right? That would be very expensive. So I'd like to find something that gets the job done, but is not going to be exact. Once I found that, so I went to McMaster-Carr and found it, I went back and I checked. Because I don't have the exact same thing I was looking for, I need to do some simple checks here, like checking again that this is actually a usable spring, okay? All right, so that's walking through the problem. I'm going to go back to the slides now. I want to highlight again, if you're looking at your result that you turned in, you know, your attempt on class participation, and you're like, man, I didn't get much of that. That is okay. That's expected at this point in your education as an engineer. You will get better at it. It takes practice. So I will tell you that probably these kind of things didn't cement for me until I was a junior or senior in our program. And then they really kept getting better as I became an engineer in practice. Okay, so this is hard. Using engineering theory to design a part is actually a high level practice. Again, going back to Bloom's taxonomy, okay, where we're at, the evaluate and create, this is not easy. It's not easy to look at a problem that is not stated like a physics problem, right? Physics has these canned problems, okay, you know, this is your input and this is your output. It was really hard to tell what was the input and what was the output for that golf ball launcher, right? But that's really what engineering work looks like. Okay, so give yourself a pat on the back if you even attempted that problem and put something down. If you didn't get everything exact, that's totally okay. We're going to work with more practice on that over the next couple days, okay? And then for the rest of your life. All right, so moving on to today's lecture. So we're on part 2 of engineering, detailed engineering design and design validation. I'd like to, again, frame where we are in the overall curriculum for MEEG102 and also remind ourselves why we're doing this. So we are firmly here in your paper design, designing and testing, right? And that's an iterative process where you're kind of going back and forth. Part of that is going to be doing the types of calculations that I just showed you, right? Using what you know from physics, from engineering theory, to eliminate some of the guesswork in your design. Our first case study that we practiced with last lecture was around determining some of the characteristics of these bars in this Melissa and Doug wooden construction set. So we were playing as if the design team at Melissa and Doug invented this for the first time. They gave us this hand sketch, okay, and we as the engineers had to determine all of the characteristics for these types of bars, all right? And we did that, right? So what we did was a couple things. So first, we sort of ran a couple quickie little experiments there that I just showed on the document camera of me breaking these various bars, but we kind of found out that it's fairly easy to break bars that are longer. So this 6-hole bar broke well under 30.5 pounds of compression, okay, when it was in bending, and that's a problem, right? So 30.5 pounds is the compression limit per the ASTM standard for use and abuse testing, and we were under that. Okay, so the reason this failed, though, again, I want to highlight, is that it not only broke. Breaking is not a problem. You can make cheap toys, okay? Lord knows there are plenty of them, right? Cheap toys that break. But when they break, they cannot produce sharp parts, and they cannot produce parts that kids are going to choke on. So the Melissa and Doug product failed because when that 6-hole bar broke, it created sharp parts. So we put it under use and abuse testing. It failed, so we were targeting this age range. It failed at under 30.5 pounds. it wasn't the fact that it broke, right? It was the fact that it produced a sharp edge there that made us fail this product test, all right? Very important to remember. It's okay, it's not great from a sales perspective, but it's okay if things break, all right? But they cannot injure the child after they break. All right, so that's where we were, and I want to talk for a sec about the engineering theory that we used, and then how we can step that up a little bit, because engineering theory doesn't always get you through every problem, right? So what can get you through a lot more problems is CAD. So SolidWorks, which you guys have been working with all semester, and hopefully you feel much more comfortable on, is more than just a design software package. It's more than just creating those 3D models and assemblies and engineering drawings. You can actually use SolidWorks to conduct engineering analyses that are very difficult to conduct just using engineering theory, okay? And you're actually practicing in lab this week with the first type of engineering analysis we're going to be introducing to you in the curriculum. That's called Finite Element Analysis. So more on that in just a second. But let's talk about, first, let's set the stage with your engineering theory. Okay, so the engineering theory that we used last time when we were working through all those equations with those Melissa and Doug bars is Euler beam theory. Okay, so this is Euler. Okay, and Euler came up with some beautiful math to model the bending of regular shaped beams when they are not bent too much. Okay, so those are the limits of that theory. The beams need to be regular shapes and they need to be bent just a little bit. Okay, if you bend them excessively, his theory falls apart. You're gonna do a deep dive into this theory next spring in MEEG 215, which is strength of materials. All right. So we used that theory and worked with it inherently when we dealt with this equation. Sigma, which is the stress, that would be the stress on these outer surfaces, is equal to my divided by I, where m is the moment, y is the position. Actually, you can measure the stress anywhere along that line, okay? And I is the cross-sectional, or the area moment of inertia, okay? All right, so that was the theory that we worked with. That theory, again, is limited to simple part geometries. Okay, so you can calculate that I for a number of shapes, and these are shapes that you're going to see over and over again as an engineer. If you look up into the ceilings of buildings with exposed ceilings, or in your house, you may have an I-beam that runs across the foundation. Okay, that's a very common shape. It actually has a really high moment of inertia, a high I on an I-beam for low weight, which is why it's used. But any of these shapes, you can actually calculate I, and you're going to spend a lot of time in MEEG 215 doing those calculations. I'm sorry, it's kind of a pain in the butt. When you go out into real practice, you look those up in tables for standard shapes, or you actually, for non-standard shapes, you wind up calculating it using a commercial drawing package like SolidWorks. Okay, so you can do this for other shapes too. So long as it's sort of mathematically well-defined, you can determine what I is by hand. Now, the other assumption that is being made is with Euler theory is that you're only doing small deformations and you have what are called simple boundary conditions. So the bending that we did and the calculations that we did on our plate assumed sort of a one end that was held in two directions here. That's what this little triangle represents. And the other end was just kind of laying on top of this circular support here, a little roller. Okay, so this is called a pin and a roller. We're going to cover these boundary conditions. Boundary conditions mean nothing more that this is what it's at each end, okay, and what the loads are that are being applied. We're going to cover that a lot in next semester together in statics, MEEG 210. Okay, so fixed pin, slider, vertical slider, smooth surface. Okay, these are all the different types of loads. Okay, and this is the reactions that you would expect. This is actually simple. Okay, so these are things that we can solve by hand again, and we don't need a computer to do the simulations. Again, with the loading conditions, okay, we're gonna do problems like this in statics next semester. Don't be afraid; we will step our way through it. Okay, this will be sort of towards the end of the semester. Both of these problems actually, but these are conditions. These are loading conditions that we can well define. All right. Now, life is not that simple. So most of the time when you're trying to determine stresses within an object, the object itself is not a simple beam, and the boundary conditions, the way that part is being held or loaded, are also not simple. Okay, so if you think about a bike, here's this beautiful fixie bike, okay, and I look down at the bottom bracket here. Okay, that bottom bracket is experiencing a lot of different loads. Okay, there's load being placed on these pedals by your legs. That's going to be transmitted down through that bottom bracket. Okay, there's also bending that's occurring. There's tension or compression in each of these tubes there. So that leads to a very complex loading situation down on this part. And you'll notice this is a zoom in of, this is actually a zoom in of a bottom bracket on a bike. And you can tell it looks like a SolidWorks rendering, right? It looks like a rendering or a solid model image, but it's got these grids on it, and that's kind of funny, right? Well, what's happening here is these grids are actually the grids that are being used to run finite element analysis. You may have noticed when you're doing your Lego model, your Lego FEA in lab, that it first does something called laying down a grid, okay? What's happening there is it is basically Legoizing your Lego. It is making this complex 3D shape into a series of tiny little blocks, and these blocks can be kind of funky, okay? They can sort of be cuboidal in shape. They can have curved edges to them and be kind of warped, but don't get me wrong, there's still a block, right? There's still a little block of material that looks like this. And each of those blocks mathematically has what are called nodes. So there are points in space that are representing the edges of that block. That is a little block of material from a mathematical perspective, and that material we can actually model how it's going to deform. We can use the equations, which you will be introduced to these in MEEG102, okay, but basically the relationships between stress, which is force per area, and strain, which is stretch per unit length, okay, the relationship between force and stretch in each direction, x, y, and z, of that little object. What finite element analysis does is it basically breaks down the problem into the stretching of those little cubes. Okay, how do each of those cubes stretch when they're being deformed in a certain way? And then it stitches the cubes together mathematically. So what winds up happening is actually quite complex. So the math behind this is the subject of several 800 level, so doctoral level courses in our department. You could take courses on finite element analysis and learn all the math behind it. It's quite beautiful. But fortunately, all of that math has also been incorporated into our CAD package, so we can actually just kind of take advantage of it, right? So the way that SolidWorks has packaged it makes it fairly easy for even folks who are just learning about computer modeling and just learning about solid objects and stress and strain to be able to work with that, and that's really important. So know that behind the scenes what's happening is this complex math where an object is divided into these little cubes. Each of those cubes has a material property associated with it. So in this case, this would be an aluminum or steel frame. And it's basically defining the stretch and the pushing or pulling that's happening on those little cubes. Okay, so finite element analysis is a really powerful tool for approximating stresses in complex structures. This is going to be the standard. This is the standard way that things are designed, okay, out in industry. They are modeled in CAD, and then there is a FEA analysis that's performed if your object is actually a solid object that's going to undergo any load. So let's take a look at some examples. Let's say this is a bracket, and that bracket is supporting a lot of weight at its end. Okay, so it's fixed on the wall, and you're going to load it way out here. You would look at maybe the stress profile because you're worried about it breaking across that center hole, right? So that would be an analysis that you might run if you were concerned about that bracket breaking. Here is, this is the guts of a mechanism, right? And so this is multiple parts that are put together. Excuse me. So FEA, you can do it not only just on parts, but you can actually run it on whole assemblies. And then you could look at each part within that assembly. So here we've got some concerns about this particular part breaking in the middle. This one, it's looking particularly bad near the ends, right? Okay, this is actually a stent. So this is a cardiovascular stent. When I went to grad school, I actually worked with some people that were modeling stents, and stents are very interesting. The material is what's complicated about a stent. The geometry is not trivial, but it's fairly straightforward. But the material within a stent is usually a shape memory alloy, which is a complex type of material that you need to really use some sophisticated computer software to program. But this goes inside your arteries, it expands out and keeps those arteries open. Okay, you can also do it for medical imaging. So actually, my doctoral work was looking at modeling the human spine and modeling when failure would happen in the human spine. So I did a lot of finite element analysis based on CAT scans or CT scans. So this type of image here would generally be generated by a CAT scan, which is a three-dimensional X-ray. You can then import that, that data into a solid modeling package. They're a little different than SolidWorks. You generally don't bring it into SolidWorks. The industry standard is a company called Materialize. You could look them up, but they do beautiful medical-based imaging that you can then manipulate and you could put loads on it, okay? All right, so FEA is the industry standard. To run FEA, you need a couple things, and let me highlight these for you. The first thing is you need your solid model. Fortunately, you guys know how to do that. Next thing you need are material properties assigned to that solid model. So you want to make sure that you're assigning a material to your solid object. In Lab 8, we have you assign the material ABS, which is a plastic, to your Lego. Okay, Legos are made out of ABS. This bracket here, let's say it was made out of steel. So I would want to assign steel in SolidWorks, steel material properties to this object. That would prescribe certain material characteristics, right? This is the Young's modulus, which we dealt with a little bit in MEEG104. This is something called the Poisson's ratio, okay, which you can ignore until MEEG215. And this is the yield stress, which we've been dealing with in this class, as well as a little bit in 104, okay, but you'll get a heavy dose of coming shortly. Okay, so by assigning the material, you're prescribing these values. The next thing you need to do is apply boundary conditions. So that's basically how your object is being held. So we're going to hold fixed this back surface back here. That's what these little line means, hold fixed. And we're going to apply a load, F, here onto the object to load it. So those are the inputs to FEA. The outputs wind up being stress, and that's usually represented in the form, it could be stress actually or strain, that's usually represented in the form of what we call a contour plot. So it's going to show you the solid model, and then it's actually going to lay on top of it images of where you have high stress or high strain, okay, and images where you have low stress or low strain. So red here, usually the way you have it prescribed is red is a place you're concerned about, blue is something that you're not, so hot to cold, okay. And then I showed you on lab number 8, basically how you can also map this in terms of factor of safety. Okay, so factor of safety would be relative to your yield stress of the material when the material starts to fail. All right. So those are your inputs and your outputs. I want to take a moment here though and just highlight, unfortunately, because we are not in person, you guys don't get to actually crush your Legos. And that makes me very sad because I spent a lot of my career, I am an experimentalist. While I can do some simulations, some finite element simulations, I know their limitations, okay? So theory is not reality. These computer models are not reality, okay? Computer simulations are going to give you an approximation. Back of the envelope calculations, your engineering theory is going to give you an approximation. But reality is reality, okay? So actual testing, physically taking measurements on goods, that's probably your best bet. But a lot of times you can't afford as an engineer to make 50 million prototypes with infinite little variations. You want to run some simulations to eliminate some of the guesswork, okay? But reality is reality. So I want to run you through Melissa and Doug construction set in a box. I'm going to show you a couple slides where we've basically crushed, we've compression tested those parts in an experiment versus what it would look like to run a finite element simulation of those same parts. So first, let me give you an orientation to what you would have worked with in the test lab, which is MEEG Spencer Lab Room 122. Okay, we've got these big presses in there, and you have been oriented to these in MEEG104, right? So the test frames that you're using, or that we've introduced to you for running some of the rubber band tests are kind of similar, okay? So this is the test lab. You're going to find 2 of these static frames. That's a static test frame. Okay, this is the crosshead that moves up and down. That's a load cell that's going to measure force. The crosshead, you're going to track displacement. That is Tucker, who's a student from several years ago. He's gainfully employed and a goober. Okay, and then here is a close-up of the test specimen. Okay, so here I'm putting one of those Melissa and Doug washers. We're going to load it vertically and crush it. Okay, and this crosshead, we're actually going to have it go down to do compression, but you could also run it upwards if you grip the specimen to do tension. All right, so that's kind of the basic setup. These frames that we have do 20 kilonewtons, which is a lot of force, guys. Okay, that could crush a car, but it applies that load really, really slow. All right, so I want to compare finite element simulations to reality for two cases. We're going to do these Melissa and Doug washers, and we're also going to do the nuts, Melissa and Doug nuts. Okay, so in reality, here's how the nut breaks. So this video is playing. Okay, I want you to kind of pay attention to when you start to see failure of that product. And what's happening here, if you were watching the screen on these test frames, is you would see a trace where this is loading, 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 and then you see the first break. So that first break there formed vertically. There was a split, and that would be a drop down. Okay, and now you start to see failure at the sides. You see another crack forming there, and there's a third one that's going to form over here. So it's going to hit a max, and then it's going to taper off. Okay, very satisfying, right? There are actually YouTube channels devoted to people crushing or pulling apart specimens on test frames, so you can look those up. My personal favorite is the channel devoted to crushing or pulling apart peeps, those really disgusting marshmallow things that you can eat at Easter. So have fun. So let's compare our simulation to reality. So on the right-hand side here is a close-up of the image of failure. So failure happened at 11 kilonewtons, okay, was our max there. Okay, 11 kilonewtons, and we had this kind of threefold pattern here, a vertical split and then a split out to the side. On our FEA simulation, which I'm only taking this out to 2 kilonewtons for right now, okay, I'm starting to see failure happening at angles, but it's not actually vertical. So these two lines would match up approximately, but I'm actually seeing a vertical split here in physical reality as opposed to what's predicted here. Now, that could be due to a couple things. So if I tested a bunch of these samples, I actually see splits happening in different directions. That's probably likely due to material defects. So if I have a little defect here in the hole, it's actually going to affect where these cracks start. You're going to learn about that starting in MEEG 302 next semester. You'll learn about cracks and how cracks form in materials, but it really does have an effect. Okay, whoops. In reality, again, there's variability in how specimens fail. So specimen number 1 failed at 11 kilonewtons, and it had this trifold, right, or three fracture lines that were forming. Here's another one that was a little bit closer to what you were seeing on our simulation, right? It had 4 cracks that were kind of starting simultaneously. There was a vertical split and then a horizontal split as well, and we got a little more strength out of that one. You guys know from MEEG104 that variability in experimental results is a real thing, okay? There's always variability in real life. Same is true with how things break. Moving on, let's talk about the washer. This one was super fun, so I'm going to play this video. This is how the washer breaks. So we would be loading, 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 and then these all failed with a rather catastrophic split, and it's coming. It's so satisfying watching these videos. Okay, so we've got a big split there. You see a tremendous drop off. Okay, and then one side falls off and then the other side falls off. That's actually how those guys fail. It's kind of fun. Okay, so comparing simulation to reality again, the ultimate here was 2,500 newtons. Okay, simulation predicted failure started around 3,000 newtons. The reason there's such a discrepancy is actually that these holes form what's called a stress concentration, which can be kind of hard to predict. So I would trust, again, you trust reality, you trust the experiment over your model, but the model can give you some information if you're comparing designs by model. All right, so, but you can see that, you know, the model is predicting basically a vertical failure band here, right? Okay. In lab number 8, you're conducting FEA for a fairly complex part. You guys are going to be working with Legos, okay? And I want to show you a little bit, because we don't get to be in the lab together with you actually crushing your Legos, what some of those results look like. So when you're selecting ABS plastic in your model, in your FEA for lab 8, know that what you're doing is you're essentially prescribing these material values for your Lego, okay? So I'd like to highlight that the boundary and loading conditions really do affect failure load and location. And this is true for the Legos, but basically for any part. So there are many, many ways that you could crush a Lego, right? You could crush a Lego by itself. So if I were to step on a Lego with maybe hard-soled shoes and I were to step on the top face, I would be pressing on these little nubs, and this is the type of failure pattern I would expect, right? I could also crush a Lego with another Lego. Meaning I could load it. In this instance, I'm loading actually the webbing in between these nubs. So I'm loading on the nub, and here I'm loading the webbing between the nubs. And you notice there's some subtle differences in actually the loading there. Remember that kids are going to load toys, and users in general are going to beat your stuff up, your designs up, in a myriad of ways. So you can simulate each of those. So here would be what we call on-face loading of a Lego, crushing it. Here's a vertical face load, so I'm loading it from the top, and I'm loading it from the side. I'd like you guys right now to think about which of these would be the strongest and which of these would be the weakest. So put me on pause and take a guess. Which takes the most load and which takes the least load? All right, I'm going to show some images now and some data from actual Lego crushing. Okay, so crushing many, many Legos over the years in MEEG102, we figured out that on-face loading results in crushing that kind of looks like this, total and complete smoosh. Okay, and you get 3,360 newtons plus or minus 142 newtons is typically what you get. Okay, so divide by 4, and that's about what you're going to get in pounds. Okay, so 3,360 divided by 4, 840 pounds before you crush a Lego that way, right? So 4 people could stand on that before it crushes. Pretty impressive. All right, vertically, you get about 2,000 newtons, 2 kilonewtons. Okay, and this is the type of failure mode that you get. You get this buckling of the sides. Okay, and then side face loading, you get a little bit more load. You still get buckling, but side face loading is 2,800 newtons. So definite drop, right? So this would be the strongest, and this would be the weakest there. Okay, and the failure patterns match up fairly well with what we're seeing here with our FEA simulations. Okay. In addition to FEA, SolidWorks can also perform really straightforward measurements. So FEA is a pretty complicated, sophisticated simulation, right? SolidWorks also does fairly simple measurements that can be helpful in validating your design. So this is not only for individual parts, but it can also be for actual assemblies of parts that you're pulling together. So I'm going to post a YouTube video about this, just in case this is helpful in your milestone number 9, validating your toy design. Couple things. First is SolidWorks, you can measure the volume of a part or an assembly. You can measure the weight of a part or an assembly. You have to assign a material to go from volume to weight, right? Because it's multiplying by specific gravity, or density times acceleration due to gravity. It also can measure centers of things. Okay, that's my phrasing. Centers of things are things like center of mass, which is if you were to throw an object through the air, it would actually free spin around its center of mass. It would also balance at its center of mass. A centroid is sort of like the geometric center of an object. It could measure surface area of any surface or a set of surfaces. So if you wanted to have SolidWorks automatically give you the surface area of all of those nubs together, it could do that. It can also look at cross-section. So you could take a cut as if you were taking a cross-sectional view of your part, and you can measure cross-sectional area, the centroid of that cross-section, or the moment of inertia, that I value, are all things that SolidWorks allows you to calculate that are helpful in your calculations. All right, so with this, guys, we're going to end with the class participation activity. That's all I had to tell you today in this lecture. Class participation is another design challenge that will be the first thing that we're going to talk about in our last lecture together, actually. We only have one more lecture, and then your last day of class will be devoted to the online showcase where you'll be giving your presentation. So this is basically your last, this will be your last class participation, folks. I am going to have a check-in class participation on Tuesday, so you still need to tune in, all right? But this will be the last big one that you're turning in, okay? So case study number 3, you're designing a toy that consists of pine wood cylinders with magnets embedded in each end. The general cylinder design and magnet that you've selected are shown below. The idea is that kids can stick them together and take them apart. You'd like the cylinders to stick together as kids hold them in the air, but you also want kids to be able to separate the cylinders with no more than 1 pound of force. How far should the magnets be embedded into the cylinder? Okay, so here's my little engineering drawing here, right? I'm looking for how far in. These are my magnets. Okay, this is the magnet I'm going to put in there. What is this distance? How far inside should I make that in order to get that type of functionality where it'll stick together when kids are holding them up in the air, but they can pull it apart with about 1 pound of force. All right, so see if you can tackle this problem, and we'll start off our next lecture with discussion about that. Okay, guys, thank you very much.